All right, today is an extension lesson. First thing I want to point out is this stuff is not expected to be on our EOC, which is why we're doing it after our quiz. However, it fits really well into the work we've been doing with exponential functions and logarithms and makes a good connection to the natural logarithm. So, objective here is to model real-world problems using the continuous exponential growth formula. I'm going to set this up just with a quick turn and talk. We did this in class. But if you're doing it later, it's a really good kind of idea to build up. So first off, let's say a bank account pays you 5% interest every year. How frequently do you earn interest? And what happens is, year zero, let's say you start with $100. Okay. At the end of year one, you're now up to $105. Okay. Because that interest kicked in at year two. You are going to bump up to, You're going to bump up to about 110 and 25 cents. And what's happening is nothing's happening in between these points. Your bank account's just waiting for that year to hit, and then it pays you. Now, if we look at this next scenario here, though, however, where a tree grows at a rate of 5% per year, how frequently does that tree grow? Well, let's say there's year one here and you have a tree that's this big. All right, and then year two hits and our tree is this big. It's grown, and it's grown 5%. However, in between that time, it's not like the tree wasn't doing anything, right? The tree is kind of slowly growing and growing and growing and growing and growing and growing and growing. It's not like it shoots up like 10 feet at the end of the year. It is continuously growing. So that is not a situation we modeled yet, and that's what we're going to cover today in our notes with this idea of continuous exponential growth and decay. So I'm going to zoom in here and I'm going to do kind of our work together through this note sheet because we're going self-paced. We're not going through slides today. So let me highlight our definitions here in blue. Some definitions to get down. First off, the number e. We saw this before when we were talking about our natural logarithm. This is used in exponential growth, and it's going to be our base in exponential growth. It goes on forever, but normally we would consider it 2.718. But it's in our calculator. It's programmed into Desmos, so we can always just type in e. And let's remember that this is our base of the natural log ln. So when we see ln, that means we're using the base of e. Now, this is the formula we're going to be using today, the continuous growth formula. It'll be a function equal to some initial amount a. We have a base of e. We're multiplying by some growth or decay rate, and then our input is going to be up in our exponent. So very, very similar to what we've been working with in initial amount. The thing is that base is always going to be e, so what's difficult to find and what we're going to calculate today as well as set up is that growth or decay rate. Now, a couple of things about this. When k is positive, we're going to see growth. When k is negative, we're going to see decay. That's one thing that makes it a lot easier to work with than what we've been dealing with earlier. The other thing is that if k is given as a percentage, we don't need to worry about adding or subtracting from 1. We just need to convert it to a decimal. So another way where it's easier to work with. Let's dive into our example problems. There's only example problems today. The math we're doing today is actually pretty intense and hardcore. So just focused on exposure through examples, not as worried about getting practice done today. So $2,500 loan earns interest continuously at a rate of 6%. We are going to write a function to model the total amount owed on the loan as a function of time in years. So I'm going to start kind of writing some stuff, and I know my end goal is going to be a function in here. So we want to get our f of x equals some a value times e to the kt. Now, I know from my problem that we are starting with this $2,500 loan. So I know that a is equal to 2,500. Okay. And I know from this problem too that this interest rate here is going to be what our k is equal to. So our k is equal to 6%. Let's remember, though, we got to convert that over to a decimal, so 0.06. And also remember, if we think back to that definition of K and how it's used, when it's positive, we get growth, and we don't need to add or subtract 1, so we can just leave it as is right here when we put it into our formula. So what we're going to say, oh, and I made a mistake here. The way I wrote the problem, I should have x up in my formula instead of t, so kx. And I'm just going to make a quick note. My f is equal to my dollars, and my x is equal to years. Just going to make a quick note there. Then by combining my a and k here, I can write my final function. So I get f of x. I'm going to leave everything blank here until the very end where I write in my other stuff. My a value, that initial amount, is 2,500. And that k value is that 0.06. It's multiplying with that x value. And there's my function to model this. So if we want to look at this after 12 years to figure out how much will be owed, that amount's growing over time and growing over time. So we're just going to plug in 12. My f of 12 here is going to be equal to that 2,500 times e to the 0.06 times 12. So once we have that set up, we can evaluate it just like we would any other growth function that we have, 2,500 times e. I'm going to throw some parentheses around my exponent to make sure that that stays up there. We've run into that before with our Desmos. And we get $5,136.08. So 5,136. And 8 cents. So we're going to start asking some other questions with this too, to kind of see how we use this and model with this continuous growth formula. So in example 2 months ago, you had 2 mice. Now you have 18 mice. If you model the mouse population with exponential growth, then what is the growth rate? So notice how in this question, we're asking a different thing. We're finding that growth rate there. So I'm going to underline this here and know that, hey, down in the end, my answer is going to be k. We're trying to find out what k equals. So let's just kind of rewrite our formula at first. That formula I'm working with is going to be that f of x equals our amount times e to the k times x. All right, and in this case, my f is going to be mice. F is equal to mice. And my, it doesn't give us a time. Oh, no, it does with months. So my x is going to be months. Now, it looks like we start with an initial amount of 2. So I know that a is equal to 2. However, I don't know what the k is. We're trying to find that. So what I can do is decipher from the rest of this problem that, all right, I get 18 mice after 2 months. So when x equals 2, I have 18 mice. So what we can do then is set up this formula here where we have, all right, my f at 18 is equal to that initial amount a, which is 2, times e to the k power, and that's times that 2 for 2 months have passed. Now we have a formula where we can solve for k here by using our logarithms. So I'm going to start working through this. I'll throw my steps in and I'll keep it in black here to kind of keep everything somewhat sane. I'm going to divide by 2 on both sides. I get 9 equals, that 2 goes away, so I get e to the, I'm going to switch this up, 2 times k. Then I have a situation where I have a base, exponent, and an answer, and this base is e, so I can take that natural logarithm of 2k, and 9 goes inside. And then so lastly, we can divide by 2 to work our way to our final answer. And there's two ways we can represent this, okay? We can either represent it as a formula, which we're going to see the value of in later examples, our natural log of 9 divided by 2. Or we can actually come up with what that is, our natural log ln of 9 divided by 2 is 1.099. And both of those answers would be acceptable. However, the one that we're usually going to use is going to be this one. And the reason is, if we're trying to be accurate and model with growth, we don't want to round off this decimal. Notice how it goes on forever and ever and ever. When we use this in formulas, we're going to actually use that whole kind of expression there, our natural log divided by something. So moving forward, the questions we're going to be answering in 3, 4, 5 are a lot more complicated, but it kind of ties everything together. So we get a situation where atmospheric pressure decreases as we go higher. Right? The higher up in the air we get, the less pressure there is. It can be modeled using a continuous decay formula. And at sea level, the pressure is 1,013, and it decreases about 12% for every 1,000 meters. So we're working our way towards that formula where we have f of x equals a times e to the k times x. Oops, sorry. So erase that real quick. To the kx. And in this case, f is going to be equal to my pressure, and x is going to be equal to my height. All right, we know from this problem that at sea level, the pressure is 1,013. So my A value here is 1,013. And then I also know that at 1,000 meters, so when x equals 1,000, I get a height that is, or a pressure that is decreased 12% from that 1,013. So what's happening there is I get 1,013 times this 12, or times the decrease of that. So instead of 12%, is going to be 0.88%. So this would be 1 minus 12%, which is simply 1 minus 0.12. So we do that, we set up our formula where we're going to have, let's actually calculate what that is. 1,013 times 0.88. I'm going to go in Desmos, 1013 times 0.88. We get 891.44. So that is 891.44. Now let's set up my formula. I know that I have that 891.44. That is equal to my A value of 1013 times that base of E. We are solving for K, so I'm just going to leave that in red right now. And we know that that X value for that 891.44 is 1,000. Now I have a formula. I'm trying to get that K by itself. So I'm going to start off by dividing by 1013. I'll mark that over here, and then I'll kind of slide over to the left. So divide by 1013. I am going to do that math real quick. 891.44 divided by 1013 gives me 0.88. That's good that it's a nice clean decimal. That'd be tough otherwise. So 0.88. Let me kind of note that, hey, I'm coming up here now. Equals, now we get E to the 1,000 times K. Now we have something with a base exponent pair. We can rewrite in natural log form. My ln of 0.88 equals 1,000 times K. And then we can divide by 1,000 to get my K value. And so what that's going to give us is K equals that ln of 0.88 divided by 1,000. And I'm going to leave that growth rate like that. And let's look at why. If I plug that in to my Desmos, I get ln 0.88. divided by 1,000. Check out how low that number is, right? 0.0000127, okay? And it is a negative as well. So this is going to be a super difficult thing to incorporate into a formula with any sort of accuracy. So what we're going to do is when we do it, we're going to use this expression to not lose any accuracy here. So if we are writing a formula for the pressure as a function of height above sea level, now we have that f of x. We still have that same initial pressure, that 1013, multiplying by that E, and then up in our exponent, we have, let's throw some parentheses, the ln, well, let's actually ditch those parentheses real quick because we're up in our exponent. We don't quite need them. It's going to overcomplicate things, I think. We have our ln of 0.88 divided by 1,000. And I am going to throw parentheses around it now to kind of show that, hey, it's trapping it, and that is multiplied by x. So if I wanted to now find the pressure at the top of Mount Everest, which is 8848 meters tall, then I'm finding the F of 8848. Got 1013 times base E. We get the ln of 0.88 divided by 1,000 times that 8848. And all of that up there is in our exponent. So just be very careful going into my Desmos graphing. Type that in where I get, let's see here, the 1013 times E raised to, I'm going to throw some parentheses to capture this, my ln of 0.88 divided by 1,000. Close that parentheses out, and then I'm multiplying. Ooh, notice how Desmos kicked it down, so let me throw that other parentheses out in front of it to kind of help us get that. We're multiplying by 8848, and it looks like our pressure becomes 326.9 at that spot. I go back to our units to see what it was in the original problem, and it looks like it's HPA as our unit measure, so HPA. All right, so example 4 and example 5, they're going to kind of ask us to run through that whole process, but without giving those scaffolding steps. So we have the half-life of caffeine in our body is about 6 hours. If we had 1 cup of coffee 9 hours ago, how much is left in our system? So we're going to kind of have to go through that whole thing where we find the rate, we write the formula, and then we plug in what we're looking for. All right, so I'm going to kind of set it up with my general formula first. F of x equals a times e to the k x. I'm starting to look in some stuff here. So I have 1 cup of coffee. So this is going to be our initial value, and we're going to count it as cup as our unit of measure. And so that means we're tracking F is equal to our cups, and X is going to be equal to our hours. All right, and I know that the half-life of caffeine is about 6 hours. So what that means is when X equals 6, I am down to 50% times that 1 cup. So that means my F value is at 0.5 cups because that's how much caffeine is left in my body there. So we can set up that formula then. I know that what I want to do is set it up with my initial value. So A equals 1 times E. We are solving for K, so I'm going to make that red. And I know that at hour 6, so when X equals 6, I have 0.5 cups in me. So I can plug those into my equation there. Then what's nice about this one is we can just omit this 1, right? Because multiplying by 1 doesn't change anything. So I can just have 0.5 equals E to the 6K if I just kind of simplify that formula first. And then that will give me a situation where I can take the natural log. So natural log of 0.5 equals 6k. And then so if I just divide both sides by 6, I'll get a k value that is equal to the ln of 0.5 divided by 6. So I have that k value, and let's check that out again. If I were to plug this into Desmos, it's the ln of 0.5 divided by 6, you can see it's again a small, really large, or really long decimal. So I'm just going to leave it written as we have in red here. But this gives me a formula where I can write the function of x is equal to, again, that 1 cup, so 1 times base of e, and then I have my k value of ln of 0.5 divided by 6, and that is times x, and I'm going to make sure I throw some parentheses around that statement for k, so I'm capturing it appropriately. Then ultimately, we're trying to see if we had a cup of coffee 9 hours ago, how much is left. So we are going to plug in 9 here. My f of 9 is equal to that 1 times e to the ln of 0.5, divide the ln by 6, times that 9. And if I go into Desmos here to plug that in, get 1 times e raised to the power, and I'm going to have to trap some stuff in my exponent here, as we discussed earlier, divided by 6. And we can also just jam that times 9 inside that first parentheses if we want, because we're multiplying our fraction by something. We get 0.35 as an answer here, so we have 0.35 cups are remaining at the end of that 9 hours. All right, one more to go. I know this is a long note session, but keep in mind there's no practice problems. It's just kind of an extension day, hitting some example problems with exponential growth, specifically continuous growth. We have example 5 where the number of people living in a country is increasing each year exponentially, so that the number of people 5 years ago was 4 million. The number of people in 5 years' time is projected to be 6.25 million. What is the present population of the country? So the timing in this problem is going to be really tricky to work with, but let's just start writing down what we know. We know we're going to model it with that growth formula. So f of x equals a times e to the k times x. And this will be tricky. We know that 5 years ago, population was 4 million. So let's say a equals 4 million. Okay, and we'll use our units in here. We'll just write the 4. And keep in mind that this happens, this will be kind of at, let's call it time 0. All right, so then if we think about 5 years ahead of now, that is going to be when x equals 10, right? Because we had 5 years ago was our initial time, so 5 years ahead is going to be when x equals 10. We get a population of 6.25 million. So let me highlight that there. So we can kind of set up our formula here then that we know that 6.25 is equal to that initial of 4 times the base e. We're solving for k here, but we're multiplying by that 10 years to help find our growth rate. I'm going to slide this up. Let's make that kind of divide note here first. We're going to divide by 4 on both sides to start getting this alone. And actually, I have the space. Let me erase this arrow so we can kind of keep all those together. We got 6.25 divided by 4. Let's check out what that is. 6.25 divided by 4. It's 1.5625. That's small enough, and it rounds out clean where I'm going to write it in. So 1.5625. equals that e to the 10k. And now we have something we can write in logarithmic form. So I'll start moving this up here now to make it easier to see, and that step's a lot easier to work with. We have our natural log because the base is e. I'm going to leave that parentheses blank for the moment, and we have 10k. And in that parentheses is 1.5625. And then lastly, we can divide both sides by 10 to get that k alone. We're going to get a k value of ln of 1.5625 divided by 10. So that formula that we're going to use in this problem is our population at x is equal to 4 million times e. That k value then is ln of 1.5625 divided by 10. I'm going to throw some nice parentheses around that. Oh, and I got to throw some parentheses in here too. So it looks like I have one extra going on. Times x. Now, let's do some deciphering. So we're trying to find the present population of the country. The initial was 5 years ago, so we're trying to find when that present population, x equals 5. So let's plug this in. We get f of 5 equals that base of 4 times e. We get our big, nasty exponent, the ln of 1.5625. Close that parentheses, divided by 10. Tack on our other parentheses to kind of trap it, and times our 5 there. We throw that into our calculator. 4 times e to the ln of 1.562. Oops, almost had a typo there. 5625 divided by 10. And I'm going to multiply that. Oh, Desmos wants me to trap it with the parentheses, so let's make sure we do that. Got this trapped, and we're plugging in after 5 years. So it looks like this is a long way to get to a very clean number. We have 5 as our answer. However, one last thing we got to realize, we were talking in millions of people. So make sure that we note that population is 5 million people after that 5 years.